This is a simple video, and it's focused on the power considerations of testing moderated effects. So before I go into what the power considerations are, I want to review just quickly what power is a function of. So you can see in this first line, power is a function of sample size, effect sizes, and the p-value, the critical p. And so as n increases, as our sample size increases, our power increases. And there's a whole mechanism for that, so I'm not going to go into a whole lot of that, but we can just assume that sample size is important because it shrinks our standard errors. Second is effect size, and this is something we typically focus on sample size, but we don't really think a whole lot about effect size. And effect size is really where we're having problems. We have a tremendous amount of problems with moderated effects with respect to effect sizes. So as effect sizes go up, power goes up. But the real problem is that oftentimes we have attenuated effects due to multicollinearity. And then finally, as the p-value increases, that is the critical p. So if we relax our standards and we decide that 0.05 isn't really our standard for rejecting the null, that if we go to 0.1, or we do a one-tailed test, which is essentially going to 0.1, that we increase power. So all three of them are directly related to power. And so now how are these three things affected by moderated effects? And here's the simplest way to think about it. Is one, it has no impact on sample size. Okay, so we can rule that out right away. And the second is that it doesn't really affect our p-value because our p-values are going to be fixed at 0.05. So there's something in the effect size that matters. And the way we should think about the effect size is if you think about Cohen's d. Cohen's d is the mean of x1, or group 1, minus the mean of group 2. So it's a group difference here. And then it's divided by a standard deviation that's pooled. And so I'm going to just write this as a standard deviation that's pooled. And that's an important formula for all of us to know about. Because what's going to happen here? Well, that's the mean differences. Now we can also express our effect sizes with respect to covariation. So not just with mean effects or mean differences, but in terms of the magnitude of the correlation, multiple correlation coefficient, or the B's or betas. So the bigger the betas, the more likely you are to reject the null. So what will attenuate B's or betas? And what attenuates the weights are, as we talked about so far, one is the hierarchical nature of testing effects. So if we attenuate effects due to order, so if we take type 1 sums of squares and we enter in effects that we really care about later on in our model, well, there's going to be less variance in y to explain because all of the prior predictors got that variance. They were assigned that variance simply by order. And so every time we take relevant variance away from any of our predictors, we attenuate those effects and we decrease the likelihood of us rejecting the null, i.e. we reduce power. So it seems pretty obvious that by having a hierarchical testing effect where moderated effects get tested after main effects, as you saw from the nested model comparison, first you test the main effects and then you test whether there's a significant difference beyond that. Well, yeah, that can definitely attenuate the effect. So what we're getting is a decrease in effect size, and so therefore decreasing our power. But perhaps the most ignored aspect of this entire thing is not the numerator in the effect size, but really the denominator. And it's the denominator that I'm going to focus on here, because this is where I think very few people attend to statistical power with respect to measurement. the standard deviation or the pooled standard deviation, and when we're doing hypothesis testing with B's, we know that the hypothesis tests are dependent upon the standard errors. So our standard errors of B are going to be influenced by measurement error. The more error that we have, the smaller the B, and also the larger our standard errors. So it works against us by having poor measures. But what's more is there is a multiplicative effect when you have poor primary variables. So if you have primary predictors that are measured with a tremendous amount of error, that error gets magnified when you multiply two predictors by one another to get that interaction term, that moderated effect. So if we take two poor predictors and we multiply them, now we have an interaction term that performs poorly because it's a complicated relationship, and one that I'm not going to go into in this class, but with respect to assessing reliability, when you take two separate measures and you combine them by multiplying them, it's not a simple case where we just look at the weakest measure and say, well, the reliability of the multiplied of the product of those two variables, that the weakest variable will dictate the reliability. It doesn't work that way. That the reliability gets compounded by both of those variables having error. And so where measurement error gets compounded is it gets passed on to these interaction effects, and therefore we have severely underpowered effects because we have so much measurement error that propagates through our model. So what influences power the most, perhaps, is measurement error. And the things for us to consider when we're testing these models is, yes, it is important to consider multicollinearity. And we did talk about centering variables to try to eliminate some of those problems with multicollinearity. They certainly will reduce any artifact due to the combination of primary predictors into a moderator. But probably more insidious than the multicollinearity problem is measurement error. So if we improve our predictors, we will have much more powerful tests of inferential tests for our moderated effects. So power is a big issue, and there are lots of ways in which we can correct for it. We can make sure that we attend to all of the assumptions, but really what we want to do is we want to select the most powerful effects and try to manipulate the effects as best we can, and also measure them with the least amount of measurement error. And that's statistical power. And it's important for everybody to remain flexible and to think about statistical power in the broadest sense and what statistical power is dependent upon. And that's the purpose of this video. The next videos are about nonlinear effects and nonlinear moderated effects, so stay tuned for those.